I would like to introduce what is the Alfred Wegener medal. My name is Hans Thybo. I'm the president of the EGU, and that's why I have the honor of introducing today's lecturer, John Burrows. The Alfred Wegener medal is one of the most prestigious awards that is being awarded by the European Geosciences Union. We have 4 such union medals, which are given in the various main disciplines, or as we like to say, pillars of science in the EDU. And one is what is popularly described as the soft earth, and we are in the soft earth here, the atmosphere. And together with the medal given in the name of Alfred Wegener to celebrate a grand scientist with immense importance for the geosciences. He was a meteorologist, so it's very appropriate for today. But he is probably today better known as the one who initiated or made the term continental drift approved. So together with the Union Medal, we also award an honorary membership of the EDU. So this is the highest award that you can achieve from the EDU. I'll just read aloud the citation for John Burrows, and then we can hear what you actually came for instead of listening to me. So the Alfred Wegener Medal is awarded to John Burrows for developing, adopting, and applying instrumentation for remote sensing of the atmosphere, and also for initiating major advances in understanding the chemistry and dynamics of the atmosphere. So I believe that John Burrows truly deserves this major honor of the EDU. Congratulations, John. So, and now I look forward to hearing about instrumentation and atmospheric sciences. Please, John.
Well, first of all, thank you very much. This is a very important day in my life. Of course, I feel very undeserved to receive this very special award, and it's a great honor. Now, I'm going to talk to you today about some of the work that I've been involved in. But at the request of one of our doctoral students, or postdoctoral students now in Bremen, very good young doctoral students, said I should, a few years ago I gave another talk a little bit, but about my life going from kinetics and spectroscopy to space-based measurements. But I began this by pointing out, of course, that I'm very much interested in the Anthropocene. Although I didn't realize that when I started my work, because there wasn't an Anthropocene then. And what I'm talking about now is the geological timescales. We can see the Earth is 4.5 or 6 billion years old, and we've had very great changes going on. But the little bit that I'm interested in is the very recent past, and it's being impacted by a species called man, which was presented to this planet only about 200,000 years ago or so, and really wasn't very important until recently, where it seems to have become incredibly important. And that's a little bit why I think it's important to measure globally from space. I'll come back to that point. But my own personal development began in Liverpool area, Merseyside as it's known, and in my early times, you can see me climbing trees and playing around. It's very surprising that you go from this to becoming a scientist. It's a very strange random walk, but that's what I was doing. And then obviously going to Trinity College, Cambridge was a big influence on my life. And I ended up doing research there, probably more surprising for me than perhaps my supervisor at the time, a man called Brian Arthur Thrush. It just so happened, it's a lot of luck plays in life, and I started working on trying to understand aspects of stratospheric chemistry using spectroscopy and kinetics. and it was to do with the CFCs and the high-altitude aircraft work. And of course, an uncle of mine, who I liked very much, said, well, this sounds very good, but have you ever thought about getting a proper job? You know, this sounds a bit strange, but I'm pleased to say that all these years later, I still don't have a proper job. Now, at this time, under my supervision of Brian and a man called Richard Wayne from Oxford, who was later my external examiner, they sent me to a conference where I was supposed to learn some science. This was my first international conference. I'd been to maybe one in England before. Actually, at that time, everybody came to Cambridge, so you didn't have to go anywhere. Anyway, I went there, and here's Karl-Heinz Becker and Dieter Ehalt there, all important people, Tony Cox at the back, and these were people who were in fact important to my life, and probably about a third of the world's people were present. And actually on the right hand side we also learnt skiing in the afternoons. It's a very good idea. We weren't very good at it, but it also turned out that, you know, you learned a lot. There's Geert Mortgat walking back, who I later worked with. A lot of people here, Øystein Hoff, who I shared an office with later, a lot of people there who I've worked with, and probably about a third to maybe 40% of the world's people in this field at the time were at this meeting. But it also turned out they had like to have a bit of fun, so I thought this was quite a good group of people to work with. And indeed, if you can pick me out of the pictures, on the left-hand side there, that was a good time, and there was lots of fun happening, and I thought, well, maybe this is not such a bad lot of group of people to work with, as it turns out. And Paul Crutzen is there, who I later worked with over here. And that's Jeff Harris, one of my colleagues, senior colleagues at the time, and Leo Salter, all sorts of people. So I have to say that it's a very nice field that I've worked in, and there's been lots of great people to work with. And only 41 years later, I am now, or since I started research, receiving this wonderful medal. And in this respect, I would like to make a big thank you to my team in Bremen. Maybe people don't know where Bremen is, but it's there in North Germany. And it's a Hansa city, and it's where a lot of my work in the last 25 years has been based, although I've been also working with American and European colleagues. And here's our institute, and here are the people who are part of my department, the other professors, and many people who you know from giving talks here today. So it's on behalf of these people that I actually take this medal, so thank you very much indeed. I have many people to thank. I'd like to thank my nominator. I'd like to thank my early advisors, Brian Thrush, Paul Davies, Richard Wayne, Harry Radford, Tony Cox, Stuart Penkert, Paul Crutzen, Dieter Perner, Geert Mortgat and David Griffiths. I'm not going to talk about all the rest, but they're my friends. I've worked with many different organizations in the last 41 years to achieve this goal, and actually I'm very much interested in what we do next. And that's a little bit about my future. I couldn't have done this without the support of my wife, family, and friends. It turns out that the 20th of April is an important day in my life, because this is our wedding anniversary. It was also the launch of GOME, my first satellite experiment, when I was in Kourou. And so maybe there's more chance to life than scientists like to believe, more luck. Anyway, it's my good pleasure to be here, and I'd like to thank everybody who... I accept this model on behalf of our field, which has been a growing field. And now I cut to the chase and say, okay, why are we here today, and what's been going on? Well, actually, up until the Neolithic Revolution, there were only about 4 million people on the Earth, and we were hunters and gatherers. And then we started to develop agriculture, and the agriculture that we developed enabled the population to grow using primarily biofuel, wind, sun energy, and a bit of early use of coal. Like where I grew up, coal used to just come out of the ground, and people would burn a bit of it. And we moved to a population of about 1 billion at the time of the Industrial Revolution. We now have about 7.5 billion people on the planet, and the rate of growth has been very dramatic. Since I was born, there are probably 4 billion more people on this planet, and it seems that it's going to go on for quite a while. There are various predictions about how it will go, but actually we've now moved to a new world, actually, a world where I think if we go in the future to the fossil record, we will find that humans have started to dominate this time period. And in this sense, we've seen a great acceleration in the post-war period, the period of my life, because we've not just seen this world population growing, but we've seen also emissions of gases to the atmosphere from this population, which is a huge, tremendous standard of living, at least for 1 billion people. Maybe 6 billion are not very well off, but in fact, 1 billion or so are doing very well. And so it's a huge standard of living and longevity of life, so all those kind of good things, but we are actually pumping massive amounts of pollution into the atmosphere. And it turns out this is what I've been working on for most of my life. And you'll actually see the number of McDonald's restaurants has also been expanding at an exponential scale in this period of time. So we've had this great acceleration. So the argument about when the record really should begin, this new age, which you'll see Paul Crutzen in particular, my mentor and former boss, wants to popularize this name. There are a number of other people. There's some great discussions here in this meeting about the Anthropocene. It's a hot topic with geologists about when it actually begins, but I think the important thing is that it probably has begun and we're now in it, and we're in a critical phase. And in this respect, I'd just like to summarize these first thoughts by saying that, repeating what I've said in a little bit, we've moved up and in population and in pollution going to the atmosphere. And in particular, we have both short-lived climate pollutants, as they're now called, which include ozone and aerosols and those kind of gases. And we have long-lived climate pollutants. We've also have a long history of air pollution, which I'll also be dealing with briefly. And surprisingly, as you'll find out in a little while, one of the first anthropogenic or Anthropocene influence was actually in a place we didn't expect to see it at all, above the South Pole where nobody is living, and that's the Antarctic ozone hole. So my view is that we need global measurements to be able to understand the science of what's going on. That's driven, curiosity driven, which scientists like myself and like everybody here are love. It's our joy, finding out how things work. But possibly more importantly is this provides the evidence base potentially for the development of environmental policy. And that turns out to be a very important societal role. So it's very important that our measurements, whether in the laboratory or in the field, are accurate and we make the right deductions to be able to hopefully at the end of the day manage this planet. And that's why I think we need a space segment, and that idea, having spent already 10 years and being very excited and by kinetics and spectroscopy, led me into field measurements. First of all, actually measuring in situ measurements, but then with the support of in particular, Dieter Perner and Paul Crutzen, I managed to start proposing ideas to measure from space. And in particular, the tropospheric measurements, as we'll see, are actually extremely important. And at this meeting, when I first talked about these things, there was nobody talking in Europe about satellite measurements. I went to early EGS's one in Barcelona in 1989, and I think I was the only speaker to mention these sorts of things. But I'm pleased to see, and it's very encouraging to see old friends, of course, but the number of young people at this meeting talking about lots of details. So the posters and the presentations I've been to have been absolutely fantastic, and I have a feeling they can all do it a lot better than I can now. So that's a very good thing in general, and I'm glad that's the case. Anyway, this is the driver for my work, but what was the first motivational issue? And this is what I started working on, and I'm going to talk a little bit about it. This is the success story, because all those who worked, and there are many fathers of success. I have the good fortune to know many of them, and many of the people in the room have been involved in this process as scientists, at agencies, working for WMO, working for European Union, United Nations, etc. This is a very important task, and this is the hope, because actually after the discovery of the threats to the ozone hole, actually policy has been put in place which we hope will eventually remove the problem entirely. and in general seems to be going along that way, but it is not a solved problem, it is a problem which has begun to be solved. Now, when I actually went to grammar school, this was we were still not too far away from this understanding, which was by another Trinity College man, actually Sidney Chapman. He invented this explanation of his friends, whilst in Oxford, of his friend's measurements of ozone, Gordon Dobson, and made the so-called odd oxygen cycle. The point about this is that the O plus O3 reaction here, which balances the production, actually was a guess by Chapman, a very good guess, but it doesn't work out quite like that. You have to have more complicated catalytic reactions which deliver that. And these were, first of all, by Nicolay and Bates with the so-called HOX reactions, but then very importantly by Paul Crutzen in particular, but also Harold Johnson. They were very interested in particular, Johnson was pushing the issue of stratospheric planes depleting, planes flying in the stratosphere depleting the ozone layer. And actually, when I worked as in the lab in Cambridge, I studied one of the first people to study the reaction of HO2 plus NO, and that turns out to change a very important reaction because its speed is such that actually you make ozone up to about 30 kilometers with NOx emissions, and above that, for various good reasons, you decrease it. But so that was how I got into this game, supported by a studentship which my boss got, Brian Thrush. But anyway, in this game, a very important step was, of course, the Molina and Rowland, and they later won the Nobel Prize. I apologize for any spelling mistakes here, the couple I see now. But Shanklin, Gardner, and of course Joe Farman sadly left us, along with Sherry Rowland a few years ago, in the last few years. He came up with the discovery of the century, or they came up with the discovery of the century, which is the ozone hole, as shown by this depletion above Halley Base Station, which Joe had put in. And together then with the work of NASA, Goddard in particular, using the first satellites, these ozone holes were first observed. So these are all people who influenced my early life and were very inspirational, actually. I'm very fortunate to have known them. And of course, it was a great pleasure when three of them at least, you can only have three people winning Nobel Prize, won this Nobel Prize for Chemistry. And so that, in 1995, of course, we didn't know that when we were all working together who would win these things. But this is now the situation that we have in the stratosphere, where these chlorofluorocarbon compounds go into the upper atmosphere, released into the troposphere, transmitted to the stratosphere, and are then converted. And in the normal world, on the left-hand side, you have these HOX, NOx, and CLOX cycles, as they're known. So these are turning over and converting. So these long-lived gases are converted into, like the CFCs, react up here because it's more reactive, and they create chlorine and OH and NOx and whatever. And this is the normal situation on the left-hand side. And in fact, that's resulted in maybe 4% depletion of ozone now at mid-latitude, so a significant amount. The double of that is what the UV level at the bottom is of UVB, and of course UVB is a cause of cancer, skin cancer. So, you know, it's a clear issue which needs to be resolved and needs to be resolved. But well, the big surprise was the chemistry on the right-hand side, where during normal conditions, these so-called reservoir species are, in the normal situation, prevent further decrease of ozone. However, in the ozone hole conditions of a polar vortex, which is very cold, and you have polar stratospheric clouds, you have the situation on the right-hand side where you have additional catalytic removal cycles which remove all of the ozone, more or less, below about 26 kilometers in the southern hemisphere in spring. This is a remarkable phenomena, and the question is, what would it be in the north? And I'll come back to some results of that. But anyway, that's something where now I think we're looking at, the chemistry hasn't changed much in the last 15 or so years, possibly a bit longer. There was a great deal of work by the community in the 1985 to 1995 period, in particular in Europe, but the contributions of Susan Solomon and various friends in the US, and the campaigns from NOAA and NASA are never to be forgotten. Now, another area that my motivation for me is to understand air pollution. In fact, this is not a new phenomena. King Edward I of England tried to ban the burning of coal in London already in the 13th century or so. In the 1950s, we had the Clean Air Act in Britain. I'll come back to that. London smogs. The word smog was actually invented by a Belgian, bringing smog and fog together around the turn of the beginning of the 20th century. And we're fortunate in Europe to have this UNECC convention called the Long-Range Transboundary Air Pollution, and its successor, HITRAP. And I would say this has been a partial success because at least in Europe and North America, we have got improved air quality. The European Union, on the Treaty of Rome, has one of its objectives is clean air for its citizens. And it still surprises me that about 6.7% of the people die of air pollution every year. Some of it's indoor pollution, but I think outdoor pollution is also estimated now to be of the order of 7 billion a year. These figures are from the WHO, so you can check back on those things. But that's a lot of people, something like 40, 50,000 Indians, for example, just taking one figure out of the blue. But these are drivers to why we need to get cleaner conditions. It's surprising that so many people are actually being affected by it. And here's the type of pictures, and there are different types of smog. The winter smog of London, which is shown there in the picture from Monet, where you can hardly see the sun and the Thames and the Houses of Parliament, and from the 1952 episode, which caused, I think it was 4,000 deaths in London, and that caused the Clean Air Act. But in Los Angeles, already in the 1948 sort of period, there was a new summer smog. And that's different in that it makes ozone. Both have particles, and that's why the visibility is so low. You can't see the ozone here or the other acidic contributors, but you can bet your boots that they're all actually really bad. So air quality is an important thing. Beijing, the Taj Mahal here is a nice picture of smog over that, and Paris. And the point is, pollution has gone from being simply a local phenomena in London to being a worldwide phenomena. And just as an example of that, Spitsbergen, which is one of the cleanest places in the Northern Hemisphere, apart from a little bit of local pollution made by the scientists who work there in summer, mainly, and a few overwinterers. But look at this, just a few days later, you've got a huge smog in the Northern Hemisphere. And so we've got global, pollution now scans all the scales from local to global. Now, when I started again in global tropospheric chemistry, this was our understanding of global tropospheric chemistry. It was basically a bit of stuff at the bottom and ozone coming in at the top and being deposited at the surface. Now, this is what we have now, okay, and this is very complicated, lots of I'm sure you understand it all, I'm sure you learn this, the younger people learn this on the mother's knee nowadays, while taking milk or whatever, and this is all these production and loss mechanisms. It's really complicated, and there's lots of non-linear issues. And on the right-hand side, we have a fairly simplified view of, in fact, aerosols. In fact, yesterday from my nominator, Maria Kakadu, we had a wonderful talk which had a large focus on organic aerosol. And that's not even in this picture at the moment. So this has become a very complicated place. But the effects of all these things need to be understood, and that's why we need both the understanding from the lab, from the laboratory, and our understanding of the processes which dominate the production and loss of these things and enable us, hopefully, to control them. And just putting on top of that, there's climate change. So here's temperature changes. These change, the rates of reactions change, and as a result, we can move the situation around. It can be better, can be worse, but basically chemical reactions are very temperature dependent, so we have to take that very clearly into account in our models and prediction of future benefits or adverse conditions being generated in the future. Okay, finally, well, it's not a surprise I'm going to mention climate change. That's a huge number of talks at this EGU are related to our understanding of both short-lived climate pollutants, as they're now called, and, of course, the long-lived greenhouse gases. Okay, and these are the changes in these are what we think is playing a particularly important role in changing temperature. And for example, here's two examples. Here's a recent temperature record from NOAA. our best evidence, which is showing since 1950. Again, what I'm saying is perhaps a time to begin the Anthropocene. And on the right-hand side are maps of ice from my Bremen colleagues, the IUP, who are using satellite measurements to observe the changes in ice. And we all know that, in fact, Sherry Rowland said this could be the ozone hole for climate science, the loss of ice in the north, because it's clearly complex, but we are seeing rather dramatic changes over a short period of time, like 30 years. So the difference of the ice, so that's the ice level actually on end of last year, or in September last year, and those are comparison curves. The point that I'm making is that we've seen dramatic losses. The funny thing is in the Antarctic, it's not quite the same. There's both, some parts of it are growing, some are not. This is already complicated. But my point that I'd like to make is that these are consequences of changing atmospheric composition, and that's why we need to measure atmospheric composition globally. We've already seen that we need to understand the stratospheric composition and follow it and check how human behavior and natural phenomena are influencing it. But this is, of course, these famous curves, Keeling-type curves on CO2, coupled with, in the more recent times from 1957 onwards, coupled with ice core data going back into the past. And here's the Keeling-type curve now, continued also from NOAA, a wonderful set of data, and you can spend, there are probably, people have huge amounts of time interpreting these data, but the point is that both methane and CO2 and actually N2O and others are all changing, and I just want to make that point. Now, it turns out CO2 is dominant. This was already said in the IPCC very clearly, possibly in all reports, assessment reports, but very clearly in the fourth report in 2007 or so, when in fact the IPCC and Al Gore won the Nobel Peace Prize for their work. So there's one, I'm going to focus later on carbon dioxide and methane. Obviously we'd like to get, and there are satellite measurements of N2O coming along, but I think CO2 and methane are a little bit further along in what they can do. We'll hear about that in a bit of time. Now, where does CO2 go? Well, amazingly, in 1960 we were producing a lot of ozone. We've gone up by a factor of 3 or so at our emissions, and it's still that 50% is staying in the atmosphere, and the ocean and land surface is taking out about 50%. So we're very grateful for that. Otherwise, we'd have been in hot water a lot quicker. Nevertheless, we have to understand how the system is changing. In the long term, it seems that the ocean dominates, but in the short term, in particular the land, which responds to changes in precipitation, whether or not the trees will be growing, the vegetation, how much is taken up, that's a big issue. So for CO2, we have a large lack of understanding of what's going on, of what's going on now and how that will change in the future. In this context, how are the sources and sinks are changing? How much is emitted and where? It used to be said, well, we know where it's being emitted, but I think actually we don't know that well enough. We have a good idea where a lot of people live, and that's certainly true of lodges, but how much is actually being emitted? We do know how much oil maybe is being burnt, how much coal, etc. For all this measurement system, a few years ago I proposed at a talk to ESA that we have the Burrows tax, which is a 10 to the minus 4 tax on a barrel of oil, coal, gas equivalent. And if you had this tax, we'd pay for all the measurement systems by a factor of 10 too much, okay? And we would all be very, very busy. So you would never notice that at the petrol pump or on your bill, okay? So it's really about political will to create the systems that we need to be able to understand these sources and sinks. And both CO2 and methane are being changed by large anthropogenic modification. In the case of methane, it's more complicated in a sense because the loss process is by reaction with OH and a little bit of chlorine and transport to the stratosphere, where it's then removed by radical chemistry in the stratosphere. But we have wetlands, we have emissions from volcanoes, etc. And there's a whole, on the input side, we have to understand this, and we have the new emissions, which is the release of methane from leaks. I'll come back to that a bit. And there's a lot of uncertainty about these, and uncertainty about how they'll change in a changing environment, in a changing Anthropocene. And those are things that we need to know, and that's my message to you all, that we need to understand these things better to be able to provide evidence. This curve, I was in a meeting this morning where we were talking about this. This is not understood why methane went up, slowed down, and came back down again. That's the measurements. And that's because the measurements are brilliant. They're extremely accurate, but they're probably sparse in the sense of we can't find exactly, or we're not doing enough of them. We're doing a great job, but we need to have better measurements in terms of coverage. The accuracy of these measurements now is unbelievably good. But why is it going across? Why is it slowing down? There's lots of theories about that. I just want to come back to the point. One thing we can do here, that I've shown this already, is that we can make measurements from space. And if you're going to make measurements from space, to add to this, you can have to think about the timescales. Now, this shows a picture where you can see the timescales roughly sketched in for atmospheric pollution. So these are short term in the left-hand side, and you have the space dimension that is going from 1 kilometer to 10 to 100,000, and on the x-axis you have time. And basically we know this. We can go outside here, and in 20 minutes the weather can change and the pollution levels change dramatically. In the stratosphere, it's more like maybe a day. There are diurnal variations which we need to think about, but maybe twice a day measurements would be enough. And in the upper atmosphere, sometimes a little bit more often. There are some tides and stuff, but essentially, particularly down here in the surface, we need to take diurnal variations into account. So how do you do this from space? Well, low Earth orbit provides you sun-synchronous or sun-asynchronous measurements. So that means at the same time, or at a slowly drifting time, when they cover the globe. So the satellite flies around the Earth and the Earth turns below it. Alternatively, you can go to geostationary, and then you move with it, and you can scan, so you get about a third of the Earth. So what we're thinking about is the system that we need is a mixture of LEO and GEO. There are some optimists from NASA who've put to the so-called Lagrangian point 1, where the Earth turns below you once every 24 hours roughly. But that's requires much bigger instrumentation, which is much more costly. So I think probably the meteorologists who got going here first, and now atmospheric scientists and climate scientists, what we need is a good mixture of LEO and GEO. And that's the thing that I've sort of been involved in, at least the beginning phase of it. And in this sense, I just wanted to make a few highlights. This is a personal highlights, but shortly after I was born, Sputnik took off and I don't remember seeing that or hearing it, but I do remember some things from that sort of age, 1957. But I do remember a lot of other things that happened after that. But the space age was, in the 1960s was this space race and the trying to get to the moon. But it's actually forgotten that already the first American satellite discovered the Van Allen belt, which is shortly after it. So actually, the space agencies have always been trying to work on making atmospheric measurements and exploration and manned flight, very important things in their own right. But actually, Earth observation has always been very fundamental to it. The Canadians were the third nation into space. The Europeans were still stuck with the post-war problem. Obviously, a lot of very good rocketry people had gone either to the USA or to the Soviet Union. Whether or not they really wanted to go is another question, but so there was a technology drift that way, and both of these teams, shall we say, were then forging ahead, and Europe took a bit of time to get going. I remember the Blue Streak rocket starting in my youth in Woomera, and with the first European rockets, and I have to say the Blue Streak usually did a good job, and then something failed later. There were a lot of false starts, but this was the beginning of what we now know as the European Space Agency. It took them a bit of a while to get going because of the political consents, and this is why it is very good that we work together, but eventually it happened, and then we started to get, for example, Meteosat, so meteorological measurements, and that came from ESA, which is now spun out into EUMETSAT. So it began to grow, but we were behind. Now, this was also an opportunity for us because at the time when I started getting involved in this in the early 1980s, there was opportunity to propose things. And we've actually had a pioneering age, possibly a golden age, where we've gone through testing and using a lot of stuff, obviously at NASA, Also, the Soviet Union in the early days, perhaps after the economic issues, then they slipped back a bit. But Japan has come on board. There are many space stations, space nations now, but the NASA and then I think also the European contributions have been excellent. And I want to talk a little bit now about European contributions, which I've been involved in. Now, here's a long list of things, but I'll just summarize it by saying when I started in 1984, we had really no idea how to deal with agencies, but there was fortunate because some of the people at the agency, there's a man called Chris Reddings in particular, who was very helpful, and his boss, Phil Goldsmith, had been on ICA-CGP, a commission, and they knew about ozone. Phil had worked with Dobson, for example. So you had these connections into the atmospheric community. They're all very good meteorologists, but they said, oh, we should try some of these things, and this climate, these pollution and climate gases we should go for. And after the discovery of the ozone hole, there was a real shift, because there was a view, particularly in Germany, is we have to do something, okay? And there was an opportunity to do a satellite measurement. And in fact, that's what the SCIAMACHY project began with. SCIAMACHY is a German word meaning, a Greek word meaning chasing, SCIAMACHY, chasing the sky. And how does that work? Well, it's a simple idea, really. Spectrometry, which has certainly been around for a long time, Fraunhofer being one of its great heroes in spectroscopy. And what we want to see is the spectra of these species on the left-hand side. There's a lot of gases, and we want to see also scattering phenomena by gases, air, and by particles like aerosols and clouds. And if we can look at the spectral absorptions and spectral scattering patterns, we can then derive the amounts and distributions of these things. And that's the basic idea which many people had started this before me, but we've tried to use the solar spectral region because this also goes right down to the bottom. It doesn't perfectly go down to the bottom always because of scattering. For example, at 350 nanometers UVA, if you're sitting on the beach, you get an awful lot coming from the side of you, not just coming directly from the sun. So we have to take, that means we have to deal with radiative transfer. And that's where I have very clever people working for me who are able to develop radiative transfer models in order to be able to interpret it. So there's a huge amount of work once you get an instrument to actually understand these things, and this is what remote sensing is all about. One important day in my life was the launch of ENVISAT. It was, I say, the second launch. We had a big party, and we very much enjoyed it. And we're very fortunate that all of our instruments have not ended up until now in the North Atlantic or South Atlantic. So there's a big risk when these things go off. This was the first Ariane 5 that actually worked. The previous ones had blown up or had not made it. So we got it up there. And now we have its precursor GOME, which was only in nadir. SCIAMACHY is important because it does nadir and limb measurements. I'm going to talk a little bit about that. We had the GOME2 follow-on, and we're going to have Sentinel-5 precursor, hopefully at the end of this year, and Sentinel-5 on working from 20 to 25. So we're improving it. Of course, the agencies are always driven by budgets, and it's a big problem whether you really get the performance you want, and I'll come back to some of that. We're still pushing forward. Our first experiments were not good on spatial resolution. We're limited by such matters. And also the sampling is non-perfect. This is essentially first semester physics. You need to sample enough and you need to have the right spatial resolution, and then you can really get things out. And that's one of our problems. However, we're all working together on these things, and we're looking forward to the Geostationary, which was originally Geosciences, is now called Sentinel-4. And there are many fathers of success. We have to be thankful to all, ESA, DLR, particularly for me in Germany, and the European nations, Belgium, Netherlands, etc., who contributed to SCIAMACHY and our successes in GOME world. Anyway, we now have a way forward. We have to make it better. And in SCIAMACHY, what we're short of is, of course, the limb measurements, and I'm going to talk a little about CO2 later on. But I've got some examples, and I just want to talk about some recent. We've had a very exciting winter in the Northern Hemisphere, where we had a lot of unusual dynamics, creating a lot of PSCs, and some very good papers from people in the audience here already being written up, or first of all presented and about to be written up. But it's surprising. This is a plot. First of all, there's some ozone holes, so from the Northern Hemisphere and the Southern Hemisphere. Or I don't know whether it's really a hole in the Northern Hemisphere. There's some discussion about whether it's really a hole or just a large depletion. That's not my point. The point is that This curve, which was created by one of my colleagues in Bremen called Mark Weber, who has plotting here the ratio of essentially autumn to spring, so March to September, or September to March, you get a linear plot. So you can plot the amount of this ratio, and this is from 50 to north, and you can also do different latitude bands, but you get a remarkable agreement with the bottom axis, which is the energy going to the north. So when you have a long-lived vortex, and the chemistry can go on for a long time, you have a large depletion. If you get a sudden warming, boom, then you don't. Okay, and that, for example, was this funny year. This is when we had a very unusual event in 2002. Chemistry behaved normally, just it was about half the size of normal. Okay, so it's very much that dynamics is now driving the chemistry, and I think this year we had some very interesting dynamics. We had polar stratospheric clouds over Scotland, and there's some very funny dynamics going on, which I think led to a situation. Just to say that we've got particularly low holes here, high in 2015 is over here somewhere in the southern hemisphere, a very low year. So this shows that we haven't got rid of the problem yet, although the Montreal Protocol is working rather well in many senses. But this is because there's already so much in the atmosphere, it takes a long time to clean it up. And there's this 2015 record low. So we're having unusual behaviors. The question is, do we understand it? That's why we need to keep monitoring and measuring it. And unfortunately, the pioneering age of satellites is going down, and we're losing our LIM capability, which I'm going to talk about. But this was in the middle of February. We had really quite a large depletion in the northern hemisphere again. So my message here is not that this is unexpected. It's within the boundaries, but the driver is now, do we understand the dynamics enough? And we have to understand those things better, but not stop measuring ozone and making limb measurements. Here's OCLO, which is one of the indicators, and you can see how this year, 2015-16, was a large amount of OCO. This is one of the killers of ozone, or at least partial killer. It produces, it's related to CLO and BRO. So you can see this was this year's development, and this is the average. This is work done by Andreas Richter in my laboratory, and this was the at 2000, so comparison years. So this was a good depletion year, and then it stopped. Unfortunately, it didn't go into March or April, when we would have had much larger losses if the polar vortex had stayed that long. And at the same time, the NOx was very low. NO2 in this case being measured using the GOEM-2 satellite. That's an important precursor, just not to go too much into the chemistry of it, but you need low NOx, so low NO2 and high chlorine to get these catalytic cycles going. Now, another thing I'm interested in, and this is from the limb measurements, just take that message that we get nice limb measure. This is then vertical, and this is the latitude grid. And we look at the trend of that, and actually we found something funny, which is around here is maybe where it's normal, but we found a loss and an increase in the tropics. And when you look in the total, you don't see much change. And we're relating this to changes of dynamics again. Brewer-Dobson circulation was discovered by Brewer and Dobson, not surprisingly. But what it says is that air goes up in the tropics and then spreads out in the different branches. But if you slow that down, you have more residence time and you produce more NOx. And if you remember, I pointed out that the NO2 plus HO2 reaction results in ozone production below 30 kilometers and above it. This is a case in point. So we think we're explaining that this way, but we need more measurements. And unfortunately, ENVISAT stopped in 2012, so we only have this year. Now, this is actually a little bit counterintuitive, because we expect in dynamics with more energy that actually Brewer-Dobson circulation increases in speed, and we think it does over a longer period of time. But this was a period where the Pacific was very cold, relatively speaking, and we talk about the hiatus, but I think this is just a decadal variation in the process. So we have to understand these things. It's very important, and that's what we're talking about this. And here's my explanation. This is the result of the HO2 reaction, that when oxygen atoms, they either react with NO2 and help to remove ozone, or they react with O2 molecules to make ozone. So basically this hiatus period, when it happens that ENVISAT flew in, was a relatively constant time period compared with of temperature compared with the rest of it. Okay, this is still very highly debated. This is controversial type stuff, but I think we expect decadal variations, and Unfortunately, the more skeptical would try and say, well, it's obviously, we haven't seen any increase in temperature as expected, but we're expecting large variability. It's a very complicated system, which is why we need the measurements to be able to understand these things. What about measurements down in the troposphere? And in this case, measurements down in the troposphere, I'm going to say NO2 is my example. This is the perfect gas. There's a lot more that we measure. It's really important for a whole host of things, but it's a very good indicator of pollution. And when you look at this, you see this is the tropospheric NO2. We have to take off the stratosphere. It's a little bit complicated, but when we look at this, we see the large population where we're doing fossil fuel combustion. We also see biomass burning, and actually if you look carefully you can see shipping. And these are all things that we and our colleagues, for example in Heidelberg, have discovered. And I just want to look at a few of these things. We also see outflow from the continents. And what we did do, Andreas Richter looked at this problem for me, looked at the trends. This was early on, and we saw decreases in this short period of time, which we attributed to, in Europe, improving legislation, and in China this was very much in contradiction at the time with first assessments of emissions, but we saw very big increases, and this increased further out to 2011. Now, you can look at these things a little bit different way. Here's the 96 to 2011 period where you see the increases and decreases, so Western Europe decreasing, Eastern Europe also decreasing, probably because of change of the economic system. US decreasing because of improved legislation. But the Middle East and India increasing as well. There's some nice pictures because presumably of more production or more use of fossil fuel for energy. You can do cities this way. And in the case of Los Angeles, we see a very interesting dogleg behavior. So this is the point, is that you go to higher spatial resolution, you can do much, much better and more useful things. In fact, President Obama was really complimenting us all because he was talking about the Aura, which has a spin-off from SCIAMACHY OMI on it, built by the Dutch and together with NASA, and he was overnight talking about how important that experiment is. So that shows it's getting some good publicity outside of the science community. One of the interesting things about China, we now have here 3 lots of measurements: GOM, SCIAMACHY, or actually 4, GOM, SCIAMACHY, GOM2, even 2 types of GOM2, and OMI, which flies at slightly different times, and we can understand the difference in these things. But look at what's happened in China in the last few years. I'm sure they have improved their cars and possibly also their power stations, but I actually think it's also an economic, so they may or may not be completely on top of how their economy is changing. If we look at shipping, those are the things that, again, we can pull out. There's a nice picture again from our team, and led by Andreas, showing the shipping from GOM2. And we were able to show also that shipping increasingly for the future, this is a big issue, particularly when it starts going into the north, going round where the ice isn't there anymore. This is going into pristine conditions. So this is going to change this story of where pollution is. And just to show the point about high spatial resolution, we have built aircraft instrumentation as well to try and push the field on, and one of which is called AirMap. Anja Schönhardt and Andreas Meyer are leaders on it, together with Andreas Richter and others. But here, close to Bremen, actually in Wilhelmshaven, we're able to follow a plume of NO2. So we get the pilots to do these very odd flights where they're flying around crazy. We were able to follow that. That's this particular thing. And look at this, one ship. So in principle, my point to you is that we can do this from space just by improving our spatial resolution and sampling. We can see single ships, potentially, is the future. That's what I believe. And at the moment, we're limited. If we take, that's the SCIAMACHY type pixel size. That's actually the new SP5 future, but we'd like to go to 1 kilometer or less, and I think that's doable. We just need to be able to do it. Here's this ship again. So this is a single ship, and why it's going up and down is to do with the chemistry in the plume. It's challenging, but we understand these things, but this is observing emissions like this. It's wonderful ability, but we need to do better from space and do it everywhere. Now, the last example I've got of a new challenge is XCO2 and XCH4. What is XCO2 and what is XCH4? This is the dry column of CO2 and methane. And SCIAMACHY started this business, and GOSAT from the Japanese started in 2009, and OCO2, the first OCO unfortunately landed in the ocean, but the second OCO2 has been up now for about 18 months and is making great measurements. The idea here is to use O2 measurements and CO2 and methane measurements to determine the mole, you can say the mole fraction really, of these gases, which are very important climate gases. And if you measure those things carefully, and you have to understand the spectra, so it goes back to my spectroscopic training, you have to understand all these things very well to be able to say exactly how much is there. And you need to measure it very precisely because we want to measure changes of the order of 0.1%. And the simple idea is that you measure before a forest, and you measure in the forest, and if the wind's blowing in that direction, if the forest is uptaking CO2, it goes down, if it's emitting it, it goes up. And so this is how we then measure the fluxes. So we're very interested in determining fluxes from the surface, and CO2 and methane fluxes is our target. We need models and we need wind data in addition to our satellite measurements. But you can see that we've been quite successful. This is a SCIAMACHY record. First of all, just looking on the left-hand side, you see CO2, and you see in Asia, lots of it in the places where you expect it, where it's being produced, the highs, the slightly higher values, okay? So this was in this period of time. So this is our total dry column, which we can express as a parts per million ratio. And look at methane here, and this is all to do with wetlands up here, and rice paddy fields, which is a man-made wetland, these emissions here. And you can see changes in time, which are well in agreement with our much more precise point measurements made by NOAA and national bodies of the same type, okay, our global, what is part of WMO GORE. Okay, but we see this is now a 60 north to 60 south latitudinal average, and we can see the increase. This is a result of the CO2 being released in early spring. After the leaves fall in fall, or better said autumn, they are attacked by bacteria and release some CO2 before the growing season in May comes in, and then we see a huge drawdown, okay, and that's why we have this scaling, and you can see that it's stronger in the northern hemisphere where most of the plants are. So there's lots of interesting stuff here and these sorts of things. On the methane side, this is this increase that we didn't quite understand. Now this is just my point again that, you know, we'd really like to look through the clouds. We need better spatial resolution in the future. But using what we've got, SCIAMACHY, we do actually get quite a lot of data out, and here we see this data now. GOSAT is somewhat better. OCO2, so this is this is London, actually, sorry, and this is showing the type of resolution we can get, okay? This is London, 25 million people or so in one thing, and in one grid point. We really want to move to this type of behavior, and these are different proposals. OCO2 is going a long way forward, but is still a rather small, you get 14 of these lines a day, so its sampling is not really what we'd like to have, but it's a very good step forward. Similarly, OCO has an interesting, GOSAT has an interesting pattern. But this is what we want. We want CarbonSat for the future. And we actually want a CarbonSat constellation so that we're able to measure daily, maybe 2 constellations, one in the morning, one in the evening or something. And then we can get measurements on the kilometer scale-ish if we get this. It's an investment, but I think it's well worth it. How are we doing so far? This is now a combined SCIAMACHY, GOSAT and OCO2, and we have great work on these are all different teams around Europe. This is the CCI initiative from ESA, which is led by Michael Bukwitz in my laboratory from the scientific side, and we're able to get good agreement. We're able to see from space the increase. This is 0 to 60 north. It's very important for validation purposes, so we're doing a great job on doing that. We're also able to see hotspots here, for example, the Rhine-Ruhr area, east coast of the USA, China, and we can do great studies on these things. You can look at those things up, but the point is we've got the ability to see these elevations which are a result of emissions, but at low spatial resolution at this stage. We're also surprised that we find the carbon sink in Europe is bigger than measurements on the edge of Europe, which may be being influenced, very precise measurements, which may be influenced because they're not seeing it down So this is a big debate, and there was a great talk by Max Reuter on this. He's the lead on our paper on that one and has been working on it. So that's an open debate. We obviously need to know the natural source very well. And there's some hope that we're right, because we're also seeing some changes in the microwave tree count number. This is ongoing work, okay, and it's a big debate, and hope our measurements hold up. We'll see. On another interesting thing is, if we take NO2 patterns, here's North America and Europe and China, okay, and we've also got CO2 in the same places. And when we do a weekly average, and the first of this type of average was done a long time ago now in Heidelberg on NO2, but what we always see is that Europeans and North Americans, as you can see here, have Fridays or Saturdays and Sundays off. If we go to Cairo, they have Friday off. But in China, they seem to work the way through. Okay, so it's perhaps no wonder that they're now the leading economy or whatever, or very large. But this is very reproducible. And I say, if you go to Jerusalem, it's Saturday, and in Cairo, it's Friday. You can see these things. It's very nice, and that's also what you might call human dimensions research. So on the sad side, also the Max Planck team recently showed that you can see the movement of peoples in Syria by changes in NO2. So you've got a lot of information that you can interpret. So this is hugely important information, although probably we know that things are very bad in Syria anyway, but you can actually sort of get an objective evidence on it and people moving. Anyway, one of the things is we're seeing this, what I pointed out before, is the NO2. It's probably the NO2 rather than the CO2. So we still have to understand why China emissions are changing. Let me just show again on this another aircraft experiment, which shows here at the bottom right, we have a power station, and we did one of these flights again, and this is now CO2, and we're able to follow the plume. And the idea in the future is that we measure single power plants from space. Okay, that's the idea. And this is a power plant in Germany that we managed to fly over using our aircraft. Okay, and there's a little bit shown again, a second attempt at it. And we see we need plume dispersion models, there's uncertainty, but we get very good agreement in Germany. They have to measure this very precisely, and we get very good agreement with the measurements. So we're showing that we can do this from aircraft, and we think we can do it from space. On the methane side, I come back to this unexpected growth. Christian Frankenberg, originally in Heidelberg, now at Caltech and JPL, has been doing a lot of work about this. In my lab, Oliver Schneising and Michael Buchwitz have been doing a lot of work. We're trying to understand this growth from space. There's a lot of debates about it. Maybe it looks like wetlands is now winning out. But one thing we did in this context was to look at fracking. And we were able, in the first years of SCIAMACHY, to observe fracking in the Bakken and in the Eagle Ford and also in Marcellus. And using knowledge of the wind and the plume that we were able to see in these early years, let me just get to this. We're using this method. We look at the plume of the XCO4, we average, we have to do years because we haven't got the sampling we would like. But in principle, you can use the same approach with high spatial and temporal sampling to be able to get the local emissions. And what we're able to see is that we have a 10% leak, we think, in these first years. Now, the point about methane is it's got a much larger global warming potential than CO2. However, if you burn it and make CO2, it means you're actually, this is what Britain did to improve its, or to attempt to reach Kyoto protocols. They switched from coal to gas. And if you burn it all, you're making less CO2 per joule. But if you release methane, you get an increase in global warming. So there's a cutoff point, okay? And what we're seeing here, at least according to our measurements, is that these fracking fields, at least early on, were actually very bad in terms of release. This is not a good thing. So this could be solved by money. It's probably that when you get 90% of the stuff out, you've already made a profit, and you don't want to spend the money on cleaning up the last 10%. So that's an issue for the future. Now, this is also interesting with our aircraft. We were able to see, this is the Central Valley, and what we see is a lot of methane here, which is unknown in the emissions coming out of oil fields, okay? So this was the flights. I think Konstantin Gerilovsky was driving the pilot nuts doing this, but anyway, they managed to do that, and this is a joint ESA-NASA project with a whole load of other things, and the work's just rolling out of that. But the fact is we're seeing a lot of unknown sources of methane. And the big future is what happens in the north when we get further warming and the permafrost starts to go. This is now the difference between April, June and July, September, and you see the massive increase of the wetlands. Will this produce a lot of methane in the north? This is like, could be, you know, very, very bad for the future. It could be, maybe it doesn't happen that way. We just don't know. So there's a big question mark about that. Okay, and in this context, I think we need a new generation of people. Now, I was lucky that we had a lot of experiments that I and then my colleagues and many of the audience here were able to work on and make great contributions to. But we need more missions for scientists to learn. If you're in Britain at the moment, I was also in the atomic energy research, although looking at environmental matters when I was in Oxford. But now, in Britain, if you need to decommission a plant, you probably have to hire in French or Chinese scientists, okay, because there's nobody in Britain working on it anymore. And this is a problem that we need to have the capacity in our people. So we need experiments to work on, and I think we should use the ISS. America is already doing it, but I think Europe, and here's a plan for SCIA ISS and SCIA LIM. We're always doing SCIA in Bremen, but we think we can do these things. It's a question really of the desire to have it. Of course, we need the new big missions. And in this context, I'm going to conclude and say, okay, we've entered this new age of the Anthropocene, and it's the atmospheric composition which we need to know about, which is driving the following effects. We need to know about the ice as well. We need to know about the temperature, but we need to know how atmospheric composition is changing. We've got limitations, even though we've had a pioneering age. We are showing that it works from space, but it's not a perfect system. We're just beginning to get towards this, steps towards this system. I've been in meetings this morning about this. We need a better system. We need to use what we've got, and this system has ground-based, some airborne, and space segment in it. This is what we need to get the coverage to be able to answer the questions and see whether we understand how the Earth in the Anthropocene is changing. And airborne measurements are showing that high resolution works. The loss of ENVISAT for Europe was bad, and we're fighting back to get where we have got some good things coming, like Sentinel-5 precursor, Sentinel-5 and Sentinel-4. But we need to move to this 1 kilometer. I've mentioned ISS. And I've mentioned the fact that we need high spatial resolution both for the short-lived pollutants and the long-lived pollutants in order to be able to understand the sources down at the bottom. And let's not forget the upper atmosphere. That's my home. We need to get good measurements up there as well. It's been a pleasure working with my colleagues on the SCIAMACHY project. We've had a lot of fun. We've had a lot of hard work. We've had some great successes. We've been very fortunate that our instruments have worked pretty damn well, and also the spin-offs like OMI, so that's all going really rather well, but there's much to be done. We really need a new CEO carbon satellite mission. Maybe Copernicus can deliver us this for the future. I know they're thinking about it. And last but not least, I'd like to thank all these people that I've published with, and they're all on there. I'm sure you can read see your name, but this reflects the different contributions to me, and I'd like to thank you all. It's been my pleasure to speak to you today. I look forward to collaborating with you and having some fun. Going back to my Araba meeting, which I showed, it has been fun. It's been damned hard work, but it's been great fun, and it's been my pleasure to know you all, and I thank everybody who helped me to be able to be here today. Thank you very much indeed.
Thank you very much, John, for this fantastic overview of the new capabilities that we have with observing Earth from an atmosphere from space. I think we can take a couple of questions, if there are any. Yes, please. Please use the microphone.
Anthropocene from not far away. My question is if you could say a few more words about the perfect system altogether, because there's some things we can't do by remote sensing that needs a lot of ground truthing. And where do you see the weakest areas? Where do we need to think about a bigger system altogether?
Well, to be honest, I don't think the ground-based measurements are in great shape. There's tremendous work that people have been doing, but it's often by individuals or individual groups of people who are really pushing it and showing what can be done. And then, like David Keeling, if you go to the beginning of the David Keeling curve, which was, of course, supported by Ravel, his boss at the time, but they had gaps, and the gaps because they ran out of funding. And this is the problem we all have. So it's really a question of getting a political will to have the system. Now, in terms of the ground-based, we need to have a sufficient... I'm not sure you can ever... We were talking about this morning, whether you can ever have a non-sparse ground-based system. It would be nice, but I think you're always going to have problems because of politics and whatever. The nice thing about space is that, at least at the moment, they're not shooting down our environmental satellites. Who knows in the future? But the fact is that... So I think the combination of LEO and GEO for short-lived and long-lived climate pollutants is what we need, and that has a cost. But I think it's small. Remember that when the Ayakafutl volcano went off, where many of my colleagues were measuring on it, within 2 days, European airline industry alone had saved, I don't know, 5 billion or something, because they weren't allowed to fly. So the amounts of money in this fossil fuel business is massive. And what we're talking about is peanuts in order to produce a perfect monitoring system for the ground and the earth. So, I mean, in the ocean, I don't know whether the Argo system is sufficient coverage. You're saying, no, it's good, but it's a lot now. It's 5,000. At what stage have you got enough? So I think that we need a combination, and of course we need the models to interpret it, and the models, of course, uniquely predict forward. So I think we're just at the beginning of developing a system, and it's really imperative that the politicians provide the wherewithal to be able to make the system so that you can make good policy. We don't do the policy. We're the guys, the Messknechte, you say in German. We're sitting in the lab measuring stuff. I went to a talk a long time ago by Friedrich Singer, who won 2 Nobel Prizes, and it was advice to young scientists. And he said, clean your own test tubes. And I'm basically just a guy who likes messing around in the lab. Well, I would... Not bad for winning 2 Nobel Prizes. So I think the point is, we are the people who can help policy, but we're not the policy makers. And we need the evidence, and we certainly need much more measurements and a better sampling temporally and spatially. I hope that answers your question, Anya. Thank you for the question.
Yeah, thank you very much. I think for the sake of the next lecture series that we have to end here. But should we thank John once again for this fantastic overview.